Good morning to everyone, and thank you for your time and interest in our solutions for digital rock analysis at Thermo Fisher. I would like to thank Sylvia here and Hirti and the Excite Network for letting us reach to you this morning. You should all have received the temporary license and the dataset to download. If you didn't, please reach out to me and I will send you these links. As part of this workshop introduction, Sylvia will be giving you a brief introduction into the network. So I'll give you the floor, Sylvia.
Yeah, thanks a lot. First of all, thanks a lot to Alejandra and Federico for organizing this workshop. So we are quite happy about that. And this workshop belongs to the Excite network. And I will give you a very brief overview about this network. Geertje and I, we are the project manager of Excite. And Excite is an H2020 EU project, and we are an international starters infrastructure on X-ray and electron microscopy. And our focus in this project is on knowledge exchange and facility access. So the Excite consortium, we have 15 beneficiaries from 9 countries. And the idea of Excite is to understand Earth materials and, for example, support circular economy and to foster knowledge transfer and also facility access, and not only in one discipline, but interdisciplinary and intradisciplinary. So the objectives of Excite are, on the one hand, offering access to transnational activities. The other one is joint research activities and also networking activities. DNA access, the idea of this is to integrate and provide access to X-ray and electron microscopy facilities applied to Earth materials. And we are offering access to more than 20 European microscopy facilities. Within the project, we also have 3 work packages dealing with scientific questions. And we have one which is dealing with standardization, one with multi-scale and multidimensional imaging, and the third one is about machine learning. But we are also active in networking. So the idea of Excite is to create a research community around electron and X-ray microscopy, and also to foster and create new links between the research community and the industry. And I think the most important part for you to know at the moment is the facility access, because you can make use of the X-ray and electron facilities we have in Europe. So we are offering access to 24 imaging facilities in 9 countries, and you can choose between different microscopes. And the idea is that people who have a scientific question, who wants to learn more about the materials, they can use these facilities by submitting a proposal to us. If the proposal is accepted, you will get access free of charge for the facilities. And afterwards, you submit a report for us, which we can then report to the EU. And our first call just ended a few weeks ago, but we will have a next call, which is opening soon. And if you're interested in joining Excite and you make use of our facilities, please have a look at our website. So if there are any questions, please don't hesitate to come to either Geertje or me. And if you want to meet us in person, we are at the EGU over a few weeks. We have a booth there. So come to us and talk to us, and we are happy to answer any questions. And that's a very brief introduction to Excite, and I'm giving the floor back to Alejandra. Thanks.
Thank you. Thank you. Thank you very much, Sylvia. Okay, so thank you for this introduction, and I believe we are ready to begin our workshop. So there you go. So Federico is showing our agenda. So first of all, I would like to introduce you to my colleague, Federico Gamba, who is our product specialist for digital rock analysis at Thermo Fisher. He will be doing most of the talk this morning, and I will act as moderator. So as you can see, this is the agenda of what we will be looking at this morning. As you can see, we have scheduled some breaks for you to walk around and prepare you some coffee if you need it, because it will be a long morning. As you can see, we have a hands-on part where you will be manipulating the Avizo software. If you ever get lost and lose track, please follow what Federico is showing so you don't get much behind. Just know that this workshop is being recorded and you will have access to the recordings afterwards, along with the support material Federico has prepared. So the temporary license we sent you will be valid at least for a few more weeks. So you can continue to manipulate the software, follow what you will be taught in this workshop, and you can even play with your own data. If we will be talking a lot about Avizo and the PerGeos software. So if you would like to test PerGeos instead of Avizo, just reach us, sorry. Finally, if you have any question, please feel free to write it down in our chat panel, and we will address it at the end of the workshop in our Q&A session. So I guess that's it for me. Now I'm going to give the floor to Federico, and we will be getting started with this Avizo and PerGeos journey. Thank you very much, and Federico, to you.
Yeah. Okay, so let's start. So first of all, who I am? I'm a computer scientist. I'm not a petrophysicist. I'm not a geologist. I'm a computer scientist. I'm doing training and presentation usually and support. So our software, we have actually plenty of software in Thermo Fisher, as you can guess. But today we will focus mainly on 3D and 2D for geoscience. We have other software that may be worthy to mention. So Avizo and PerGeos, we will talk a lot about them. Amira and Athena, we will not talk about it, but Amira is kind of sister of this Avizo and PerGeos, but for the life science. And Athena, just shortly, it's a data management cloud platform. So it's a place where you can store the data coming from experiment. So that's important. You know, all these four software exist. And if we speak more specific to Avizo and PerGeos, many customers confuse them or they don't know exactly what's the difference. So Avizo is a pure material science image and analysis tool, 2D and 3D, and actually also multi-scale if you like. It's not targeting a specific material, so it's quite broad and is designed to be very flexible and generic for research on any material. Indeed, any material, then if you look at the real usage, it's usually like a composite or porous media or fiber media, so the fiber material, sorry. Yeah, so that's usually the kind of material that get analyzed. PerGeos, you can think is a verticalization of Avizo specifically for rock analysis. So it's less generic. And so this gives us the possibility to customize and add more feature dedicated to rock. So we will see what is available in both software, what is missing in one of the other, etc. So at the end of the talk, we have a comparison, a more detailed comparison. And my idea was to go through some hands-on and through some real demo of the product. You will see the user interface. So you will appreciate the difference and the reason why we have two different software. Yeah, so I think that's enough for this. Okay, so this is a generic standard workflow when you are in material science. You start on the top left and finish on the bottom right. So normally, most of the workflow looks like this. You start acquiring your data with CT, micro CT, EM, TEM, whatever. Any machine that generate 2D or 3D or 4D or 5D images. You import the data in the software, let's say Avizo PerGeos. Typically, you have to do some pre-processing to reduce artifacts or to maybe align the data if they come from a FIBSEM. So you have a quite important step here. If you miss this step, then it will be more complicated to do the analysis. So it's an important part. We're not going to see a lot in this presentation about this step to make it a bit shorter. Then the first things you do, usually it's a 2D or 3D investigation of your data. So I call it visualization. It's more like a doctor looking at the images and try to understand quickly what's all about. And then up to here, yeah, you have nice picture, nice images. You could do even a video, but then you want to measure, you are a scientist, you want to get some meaning out of pixel. So what people does, they segment the data, so they try to assign pixel to objects, to meaningful part of the object. If you are in rock, most of the time you want to assign to, I don't know, pores, grains, or different minerals. If you are in a completely different material, it could be different, but you get the point, I think. And you may first just assign pixel to one generic phase, like pore space, and then eventually you may want to measure each individual pore. So you're going to split them into each entity, and then you are going to measure, for example, the equivalent diameter, the volume, the length, the ratio of length and width, and things like that. And so you can start to prepare tables out of it, and maybe histogram and charting and so on. Optionally, people want to simulate, especially in digital rock, it's a common thing, but not only. In any porous media, let's say, we have simulation available in Avizo and PerGeos, so you may want to simulate the permeability, for example. So we will see a bit of this. It's common to do that. Some people do it inside our tool, some people do it outside our tool, because they may have already their own simulator, and so they just export from here the geometry, do the simulation outside, re-import the data into Avizo to do visualization of input and output in the same place. And finally, you have a part that is important, is how to present your data, your numbers. If you do papers, if you do presentation is important. So that's the standard workflow. In material science, if you go down to specific, so material science, for example, it's rock, and for example, could be micro-CT. I focus on micro-CT because it makes sense. It's simpler, but we have workflow on full core CT, on micro-CT, on any scale, on SEM, on FIBSEM, on TEM. So I focus on this one because it's simpler for tutorials. But be aware. At the very end, I have one last slide in which I will show you other workflow. So a very common workflow, you have a plug, a micro-CT plug, and you want to characterize the porous media. So you search for the pore space. Then you probably want to differentiate the connected pore space from the pore space, because the connected one contributes, of course, to the permeability, and the not connected doesn't really contribute much. When you are at this step, you may have different paths possible. One, you just try to estimate absolute permeability, for example, with simulators, or you may want to go and split each pore and do a pore size distribution. Of course, it could be the same with the grain size distribution. And another quite standard things people want to do is to estimate relative permeability, especially in oil and gas. So that's another path. We do this with pore network modeling. So this is why you have this extra step here. So that's a common workflow. We are going to see an hands-on that will go this path. So the hands-on of Avizo will be pore space, connected pore space, separate pore space, and pore size distribution. And then we are going to repeat, but not in hands-on mode. So hands-on will be slow. I will go such slow that normally you should be able to follow me with the software on your site. The rest will be more demo style. So I will show the software, but a bit quicker. but you will see the software in action. So let's move on. So Avizo, the GUI. So first of all, I try to give you an overview of. So this is the software start running really on my machine live. It's not a video. I will try to give you an overview how Avizo is designed, how it looks like. So you have plenty of different area. The main viewer, there is usually one viewer, one 3D viewer. It could be actually put it in 2D mode if you want. So if you just select a different point of view here and you remove the effect of perspective, it will look almost like a 2D viewer. Indeed, it's not. The viewer is always a 3D viewer. In reality, we don't have a specific 2D viewer. You could have multiple viewer if you like, but many people stay with one. We can have up to 4. Here on top, you have all the manipulation of the viewer. I'm not going to show you all of them, but it's pretty intuitive. You have this hand, that means you can move around the data. Then you have this one to pan, zoom, etc. So this is not super complicated. And this one, it's a specific. If you click here, you will be able to interact with the data, but the camera will not move anymore. So if you can move back like that. What else important? You can take a snapshot. You can change the scale because the software speaks with scale. You see here. So yeah, I think you had a small cut on the line, I guess. So a second most important part is this one. This is why you design your workflow of processing. So this is an example of distribution analysis computation. So I started from the input here. That's my micro CT scan. And then I kind of did a segmentation somehow to split, let's say, the pore space and the grain. And then I compute my porosity. I did only the axis connectivity. I separate the object. This is why I see the grain here splitted. I'm looking at this data here that is the separated. This guy here and this guy here are yellow. They do visualization. Okay, so everything that is yellow is in charge of sending visualization here. What is red is in charge of computing, and what is green is data. That's roughly the organization of the network. So typically we tend to suggest people to have this layout, but you can do whatever you want, but that's the most common. So you have your data on the left, the intermediate step here, and on the right. And you can change on the fly the connection. So you can do you can hide and show stuff easily like that. And you can say, okay, show me this, show me the pore space, show me only the separated, etc. So you can change a little bit the input of modules dynamically. So that's pretty convenient. Then next important things is when you click on object, you see this guy here change on this panel. So this is following you. So there is only one of this panel per time. So if you want to change something, look, if you want to see property of your data, you click on the data, you will see some information like the type of data, the size, the range, etc. If you go on a segmentation, of course, you always have a sort of preview, a simple preview here. It's just a thumbnail. If you click on a module that does computation, you will get the user interface of the module. So this is the guy that do the separation between of the pore space. So you have every algorithm you can imagine as some parameters, so you can change them like that. So I think that's roughly the introduction. So now I think I'm going to switch back to my presentation. So as I said, we are going to do hands-on through this. Maybe I repeat it slowly because now I enter a little bit more in hands-on mode. So it will be, I'm going to speak a bit slower to let you do the hands-on. I prepare a video because I thought it's better to have it at hand, so I can give it to you later on if you get lost. But the step, if you want to compute pore size distribution, that is a sort of let's say bar chart with the size of let's say pores. The standard workflow would be load the data, look at it, start to segment and separate pore and grain, and then you will, let's say, temporarily throw away grains because you don't care about them for this workflow. And then eventually you may want to compute the porosity, the connected porosity, and then you separate each pore, you measure each pore, and then you do a distribution chart. That's the goal of this hands-on. So we have about, I think, half an hour to reach that. Alejandra will guide me if I'm too slow, too fast, but okay. So as I said, I prepare a video. So I will play with the video slowly. The video, I think it's about 16 minutes, but with the break, I will stop it. So we will probably need like 20-25 minutes to go through. I hope everybody that wants to do hands-on has the license and the product installed, so we can start. First, when you start Avizo, it will look like this, completely empty, and asking you, do you want to open a data? Do you want to open a project? Or you want to start with a blank project? I typically click on project to go basically blank. This is what I do. So you are here. Of course, the project is completely empty and you can open the data. So click. You should have received an archive with this name. Inside of it, there is a .am file that is the format of Avizo and PerGeos. It's a tiny cube inside a micro CT scan. You just double click on it. Of course, in a real life, you are probably going to import a different file format, like a raw or a list of PNG file. But for the demo purpose, we make it simple. It's a sort of simple tutorial I'm going to do today. So you double click on it. Yeah. And you should get it. By default, depending on your configurations, you could get already something visualized or not. It depends how it's configured. Avizo. My Avizo is not going to show anything by default. It's just showing the data object, and I click on it and I can start to look at it. Like this is the number of voxel, so roughly 270 by 270 by 220. It's a 16-bit min and max, etc. This is a preview. It's in nanometer because the software by default started in nanometer. I'm going to change it. Yeah. So first things, I don't like to use nanometer for micro CT, of course. So you switch to micrometer, and then all the measure becomes microns. And the first natural things you want to do is to view the data. So how do you do that? If it's not already the case, in some cases you get already an automatic visualization. But if it's not the case, you right-click on it, and you get a huge list of modules. So this is all the modules that can apply to a cube of voxels. So you can imagine you can do anything with it, like rendering, computing, and so on. So for convenience, there is a category called favorites, in which you have the most used, let's say, modules, or computation or rendering modules, doesn't matter. It's a list of modules. And so you get the bounding box and the ortho slice. That are two most useful at the very beginning. So bounding box, you maybe I hope you get it. You can or double click. Maybe I will show it again. Yeah. So you have either the option to double click on ortho slice, for example, or you can click once. You will get another panel here, and you click on create. I'm get used to double click because it's faster. But okay, for tutorial, I click create, but in real life, I double click on the module. So I already put 2 modules in my network, and this is why I see the bounding box and the slice. But you see the contrast is not very good. So I will have to select ortho slice and change the color map settings. Why it's not good contrast? Because the color map is focusing on the entire range from min to max. And probably this is not what I want. I want to focus on a smaller range where there is the histogram. So I'm going to change this color map settings, okay, to look better. Yeah, I can rearrange. You will see as the network grow, you tend to reorganize it to look much easy to understand, because otherwise you get lost. On a real project, this network can become really, really huge. If you have a complicated workflow, or you can do many projects instead of one. Anyway, so what I do, I remove this auto adjust range, because this is going to bring me every time to the min and max, and I don't like that. I don't want that my ortho slice continuously go back to. And the other things I'm going to say, focus on the data histogram, because this is what I like. So yeah, or data windows, similar. Yeah, so now it looks better, and this will stay on this range. It will not automatically, because I disable auto range. And now I can look at my data. Yeah, I save it because my idea was to provide you all the step saved. It's a good habit to start saving here and there. It's like any other software, it may crash. It's so you prefer, it's like Word or PowerPoint or any so it's a good habit that during your work you save, and you may save different step in different projects. So different. So what is this HX file? It's a file that will allow me to come back exactly to this condition. So if I get lost tomorrow, I can reload this file.
Hello.
And get. Can you please mute?
हाँ बोलिए.
People not speaking.
हाँ अभी तो चल रहा है.
So I move on. So the next things we want to do is to segment the pore space. Okay, so we want to separate pore and grains. So we will need to go to, you see on top, you have many tabs. I didn't explain them actually, it's my fault. This is somehow different task, completely different task. So project is in Avizo, you spend probably 80% of your time in this project mode, but eventually you may have to go in one of this, not all the time. The standard user spend 80% here and 20% in segmentation. It's very rare that you go in the other one. Segmentation is you will see what is it. I click. So sorry, I click in the wrong place. Yeah, it's because it's a video. Could happen. So I go back to my video, and yeah. So segmentation. So what happens if I click segmentation? You get this dialog because we are redoing this workspace. We are starting to implement a new segmentation editor. Is not totally finished, and it's going to be incrementally updated. So at the moment, for this tutorial, I prefer to go to the classic segmentation workroom. In the future, we will have what we call a segmentation plus workroom. I will explain why, but the idea is to be able to handle larger data. That's the idea. But today, this new segmentation editor is not fully finished. But we thought it's good to propose already to users, because there are some good points in this. But for this tutorial, we stay on the classic one. You can even cross-check this one, so you will not get asked again and again and again. So anyway, you click on classic, and you will get here. So this is the classic one. Maybe a brief explanation because there is a lot of panels here. So what's the goal of this segmentation workroom is to segment the data. So to split, let's say, pore and grains. It's a semi-automatic environment. You can do really manually drawing pixel and say, this is a pore for me, and drawing pixel, say, this is a grain. Or you can do, there's plenty of tool here. You can do sort of magic wand sort of style. You can do plenty of different way. You have watershed, etc. So you have really a lot of different tools to do segmentation. It's one of the strengths of Avizo to have this capability of mixing between automated and semi-automated and purely manual. It's really a center point of the product. We will see in PerGeos, this part is different. So this is why I'm spending more time on it. It's one of the big difference between Avizo and PerGeos, the segmentation editor. So what else? Here you can control display control. You control the look and feel of this viewers. So again, here we will have to probably move this back to have a better contrast. And here you have a list of materials. By default, you get only one. So exterior means everything that I have no clue what does it means. What is it? It's a pixel. I have no clue what is it. And inside is okay. It's inside. It could be the pore space, but we may need more material. At least we will need to create pore space and grain. Okay? So we will have to populate this list of materials doing add here. You can visualize them in 2D and 3D. We will see. And here you have the data you are looking at. So you are looking at the grayscale image that we load and to the segmentation that we just created that is actually empty at the moment. And then you can, of course, move this guy here, right and left, to move on different slices. You can zoom in and out here. Let's move on. So next. So I focus on my grayscale area I like more to have better contrast. And yeah, you can decide what to see in this viewer. I prefer to rename it. Why? Because what I'm going to do, it's a workflow that is called Markerbased Watershed. What is it? I guess 80% of people knows what is it, but I repeat it, is the instead of assigning myself explicitly the grain and the pore space precisely, I will let Watershed do the job. So I will just put some, let's say, tentative segmentation of the grain, tentative segmentation of the pores, and then I will use Watershed algorithm to expand these two phases, and they will meet at the border. And so this is a better way of doing it. Instead of many people just do thresholding of the pore space and move on. It's not the right way. Watershed is more robust. So what we need is to create what's called markers on the two phase, and then to do Watershed. Well, I changed the color because the default I don't like them. I changed the name, so I will call this pore markers. Yeah, I think you double click on it, or you can change the name. I add another material that I will call grain, of course. And yeah, so move on. I prefer to assign color that are more easy to see. It's not mandatory, of course. You can. So now we have to start populating this guy here. How do? I will use thresholding. So I'm going to threshold first the pore space, but not precisely. I will be very conservative because I'm going to use Watershed. So for example, something more or less the split between, just to let you know, the split between pore and grain, it's roughly around 11,000. But it's an area, if you go to 11,000, you are in an area where you're not totally sure if you are in the pore or in the grain. So we will let Watershed decide. So we go back to 10,016 something around 10,016. I check, more or less it looks a good value. And so I say, okay, this is my markers. I think I'm pretty sure this is a good marker for my pores. Okay. Didn't remember I played so long with the value. I will put a specific value, 1019. Yeah. Sorry, this part is too long. Well, anyway, you got the point. So now the tricky part, I'm still just playing with selecting voxel, but I haven't yet assigned this voxel to any of this material. So to be sure that this is going to be into the pore, I click on the pore and I click on the plus somewhere. So we will see. Yeah. So here. So when I click on this plus button, I'm going to move the selected voxel into the pore. So now these voxels are really attached to this material. I have decided that they are pores. And so I'm going to do the same with the grain. Yeah, so the idea is the same. You start to change this masking to something really bright, of course. And this threshold here, I will put it way on the right, something more than 11,000 something. To be sure, since it's a watershed, you should be really far from the other phase to let the watershed work. So same things. I select the voxels. I need to select the grain here, and you see quite a lot of click. Why so many clicks? Because this tool is very generic. It doesn't know exactly what you want to do. So it's a super flexible. You can do everything and the opposite of everything. So it's an advantage and is a disadvantage at the same time. So when you create a software that is very flexible, then you have a lot of click because it's not a predetermined workflow. So you have plenty of option, plenty of widget, plenty of button. For a beginner, this is quite complicated, but we do training. So what I did, I click on grain, I click plus, and now I have really splitted. I have my markers. Now we have to do what is called watershed. So I will click on this tool. I change tool basically, and here I have the watershed tool. Watershed require a gradient. So I click on create gradient. It's going to compute it, and then I hit apply and create label field. So this is really, it's already done. So because it's a small data, what happens is that my markers has been expanded, and now I really have my pore and grains selected. So I have a new data object. It doesn't look like from this user interface, but indeed now I have a new one, a new object. So I will rename it. It's not anymore a marker. This is really the output of my segmentation. So it's my final segmentation. So I call it labels instead of markers. And if I go back to project, you see I have, yeah, that's maybe important. You see I have two segmentation now. One is the marker. This is what I see on the screen. And one is the computed watershed. So marker, it's in a lot of area, there are pixels that are not assigned to anything. And of course, in the label, the watershed has done the job and everything is assigned. So what I do here, yeah, in the project, I have the gradient because I push on create gradient. I have the markers and I have the segmentation. Indeed, I don't need to keep markers and gradient. So if I remember well, crash it. Because what I need is only this output, the final result. So I attach it to, this is optional, but usually you attach a label to the data. And I think I will throw away the marker if I remember well my demo. move a little bit faster. Yeah, you see the difference. The marker doesn't fully assign every single pixel, and the watershed final output as all pixel assigned. So I think I throw away the markers, and so we are quite in a good position. We have been able to split grain and pores. I would like to see it here. So how do I do? You see the other point of Avizo. It doesn't automatically visualize things. It computes, but then the data is here, but I don't see it. So it's up to me to decide how I will visualize it. You will see this is a major difference with PerGeos. So I will have two instances. I have to right click on ortho slice. I will add a color wash, and I will connect the color wash to this data. So you will see. Double click, I connect the color wash data to this one, and now I see actually it's the two data blended. So I save the project. You will get this. I think I send you in the zip file, the archive I send you. You have a directory and another directory called solutions, in which you have all these projects saved. So when you will have a license of Avizo, you will be able to reload all these steps that I saved. So even if you get lost today, you will have plenty of way to redo this workflow basically yourself. Yeah. So next step is actually I want to focus only on pore space. I don't care about grains because I want to do pore size distribution. So I take this segmentation with two phases, and I will do some processing to keep only one phase, the phase that I care, that is the pore space. So how do? I right click on the two-phase segmentation. I select arithmetic. Well, I go back on the video. You see it's in the favorite. You can type names. This is how I use actually every day Avizo. I remember roughly the name of the modules. So when I right click, sorry, I think I get the next video. Yeah, so usually I right click on data. I try to catch the place in the video where I do it here. You see, I start to, instead of looking inside favorite and find arithmetic or search it through, because here you have a huge list of modules. Okay, so to find the module you want, sometimes a little bit long because you have too many. So another way is to start typing a part of the name. So I start to type here arith with H, and it finds for me 3 objects that match. And so arithmetic, I double click on it and I get the arithmetic. This speed up a little bit the way you work. You will do it not maybe the first day, but later on you will start to work like that. So I get as input the labels. What I need to do is to put an expression that say, it's a logical expression. I will say A equal 1. Why A equal 1? Because, sorry, every time video is the drawback of having videos is that if you click on the wrong moment, you switch to the next slide. Yeah, so what I'm going to write as an expression is A equal 1, because I have two phases. One is the pore space and 2 is the grain. So I want to keep only the 1. So this is, and basically this arithmetic is a generic tool. You give many inputs, you write an expression, we will compute the expression for all the voxel, and we will produce as output the same thing. So you get a result. The result is all the pixel where A equal 1 are checked and the other one are false. So you have a true false condition. So this is my pore space. It's one possibility how to select pore space. Yeah, so I speed up a little bit. I think in 10 minutes or so, I would like to finish this one. So now I have only my pore space. You see, I reorganize a little bit things around, and I put always meaningful names myself to object, because this is a simple one, but So you see the trick. This color wash was attached to the label. Maybe I try to go back. You see, it was like that. I play, you will see. I take the connection and I put it here, and suddenly the visualization update. So I'm just looking at this now. Okay, so that's a very convenient way to see stuff. So I don't remember what did I do. So now we have to go next and split the. So again, right click. You see, I don't search the module through here. I want to do porosity. So I start to type Pore and I get plenty of proposal. The one that is good is this one, volume fraction. So I would select porosity volume fraction. And yeah, so I will do apply. So this is going to compute for me the porosity 22.9%. So that's the porosity of this rock according to my segmentation. And next step, I'm going to find the connected porosity. So how do I do that? I need another module called axis connectivity that on Z, for example. So on the input is the pore space label that I'm looking here. I ask to this module, please connect a new label in which you keep only the connected pore space through Z. And so I do apply, I get another data. It's called axis connectivity. And I can compute the volume fraction as well on it. I change the name because I don't like the names. So I call it pore space connected dot labels. For me, it's more meaningful. And then right click, again, volume fraction. This one. And again, I will hit apply and I will get a new table here. So it's slightly different. It's 22.78. So it's almost all the actually connected what I found. So where I am, I have the porosity, the connected porosity. I computed both. So I think now we can move forward on, yeah, I reorganize a little bit. Maybe we can jump. Yeah, I tend to change names to things because I don't like the default names. They're not very meaningful to me. Yeah, so I call it porosity measure, etc. It's not mandatory, of course. I save, okay, because it's an important step. We have identified porosity, so I think it's a good time to save. And next, we are going to split the pore space. I jump it ahead. Yeah, so how do we? So we need to do the pore space distribution, right? So we need to split this guy into separate entity. So we need to start from this pore space connected and right click and find what is called separate something. We have to separate. So I will type separate something and see what Avizo proposed me. Okay, separate object, fine. You see, it doesn't speak about rock. It doesn't say separate pore space. It's a generic algorithm that separate. And I have plenty of methods here. There are 2 or 3. So I have to segment, use the skeleton aggressive. Why I will not explain you why, but and I have to trim some parameter like a connected object fast, and I think I can apply. I'm not going to explain you all the details. That's too long. It's a powerful algorithm that's split. You can guess that splitting pores in 3D is not trivial. So there are plenty of tiny detail that you may want to set up here. And we can do this also in 2D. So if you have a 2D SEM with the pores, we can split them as well. And there are plenty of, the algorithm is quite, it's a block. This is a block that contains many sub algorithms. So you see it took sometimes, but finally you get them splitted. So again, I want to see, I connect, and this is my splitted pore. So we are pretty near to our goal, because once you split them, yeah, so you may want to see them in 3D like that. How did I do that? I right click on the output and I say volume rendering. Okay, actually it's voxelite volume rendering to be precise, but so it's here, voxelite rendering, and you get this nice rendering. So you can appreciate in 3D how they look like. So, and so next we need to start computing the size of these entities. Yeah, I think I save. Why I jump this part. So I will save, and then we need to do some computation on the size of this entity to be able to do the pore size distribution. So who is doing the measurement? There is one module that you will use a lot of times. It's called label analysis. It's something that measures each individual entity that you have selected. Okay, so it's a very useful and powerful object and module. So label analysis. It looks simple because you have very few inputs, but it's not. It's you will see there is some. If you want to do just a simple basic measurement, you just hit apply and that's it. But for our purpose, we need to to do a small customization of the module. We want to compute equivalent diameter of each, let's say, pore, and the volume of each pore. And so then I will plot the cumulative bar chart of the volumes against equivalent diameter to get my pore size distribution. So instead of basic, I customize it. I click here, and here we are. This open a. So we have a lot of possible measure. I think we have like up to 1,000 different measurements we can do on each of these pore, and they are split into categories because there are too many. So, and when you do an analysis, you create a group of measure and you start with apply. So first of all, you have to define a group of measure you want to do, and then you can start doing it. If you use the basic, it's already predefined. You have volume, area, barycenter, and mean. But this is not good for me because I want the equivalent diameter. So the basic default is not good. So I have to create my own group of measure. So how do I do that? I click on this, create a new measure group. So, and then I give it a name, like, yeah, I think I call it Excite PSD, if I remember, or something like that. Okay, pore size distribution, you name it as you like. And then you have to populate the list of measurement here. So you have to go and search for them. So inside geometry, you have volume 3D. You double click and they appear here, and you go up, you scroll up, you get equivalent diameter. So these are under geometry because these are geometrical properties, but you have many other type of. So I define in my own custom group of measure. I can do apply now. So what this module is going to do is going to take each of these single entity and compute volume and equivalent diameter for each of them. So you will get a long list like this one. And 1, 2, 3 is the ID of the pore. You get some overall statistics like the mean, and max, the median, variance, etc. So that's already quite interesting. You could just export this as a CSV file and do your own charting outside. But we have some tool to do the distribution analysis. Yeah, so I think we are roughly in time. Yeah, so it's mostly done already. I jump a little bit ahead. Yeah, I save the project as usual. And now the last step is how do I do the chart? Again, a lot of people don't do it in Avizo. Many people just stop here and export because they want to have an Excel spreadsheet. that they will put inside maybe Word or their paper. But anyway, we have so-called distribution analysis that do the binning in a way, and then you do spreadsheet, and you will get the spreadsheet. So I don't think you are obliged to do it exactly like this. You see still many more clicks. Finally, here we are. We have got the pore size distribution. Yeah, I think my suggestion is rather to export and go through Excel, because then you will be able to control a lot better the quality of your charting, in my opinion. Of course, the tool Avizo has all the tool up to the end, but I know the real life is slightly different. So I saved this into 5. So you will have this folder with all this saved data. Okay, so you will be able to replay that. Yeah, that's it. I think I exported the maybe this is important. How do I export data into Excel? You click on any of this guy, or the label analysis or the distribution, depends what you want to export. You right click, and I will let the video do it. Yeah, sorry, it's here. Yeah, so when you right click, normally you get proposed modules to do computation, but here you have two nice buttons. This one is going to be save, and this is save as. So this is what you want to do. You save as, and you get proposed formats. Yeah, you have a list. You see, you can export in many different formats. One of them is CSV, column separated, and so you save it like that, and you will be able to just look it into Excel. That's it for the hands-on. Yeah, I don't know if you are really able to follow me, but I guess you get the idea. So here we are where we are. So I think we could have a break for 10 minutes. So the next step is to give you an overview. First of all, an overview of the user interface, and then I will play a similar video a little bit faster with the similar workflow than in PerGeos. So let me show you PerGeos. Yeah, so this is really PerGeos on my machine. This maybe we show later. So what is this project is an example of relative permeability computation done with PerGeos. So you have a similar step at the beginning. You have the segmentation, the connector per space, and then in addition you have other stuff like the Pore network. So we will see. Yeah. So, but just in general, how the user interface looks like. First of all, you notice you don't have the network editor here because PerGeos is targeting more data. It's data oriented. So you see your data here, but you don't have specifically to attach visualization to the data. The data will show up automatically in the viewer. So it's a different way of working. When you load something, the data comes here. When you compute something, the data goes here. You can move them, of course, in different categories, but it's more a project data oriented rather than network. Of course, there is the network, but it's not visible. We can say like that. We still keep the history. Every object that is here has been computed through a workflow. So this workflow is the network, and we keep it. It's not lost. So for example, if I double click on this, you see it's here. So indeed, the sequence of steps that has been necessary to arrive here are stored somewhere. But you are not going to edit this network yourself. You are just going to do things, and PerGeos will record everything you do and will create the network for you behind. So it will let you, PerGeos, the philosophy of PerGeos that you don't build the network. It's PerGeos building for you according to what you do. But is yeah. So we will see in the demo, of course, how it works. In terms of panels, it's on. So this is different. This is the same. When you click around, you get a preview of every data. And then there is another important difference is that we suppose you go through these steps one by one. So home is just the place where you see the data, but then you go to pre-processing is the place where we are supposed you will do like a filtering or artifact removal. So here you will get proposed only the modules that make sense if you are in pre-processing mode. You will not see here any modules related to segmentation or label analysis, etc. So in a way, the software tried to guide you more than Avizo. So you are more constrained in this. Since you are in this step, you will focus on something rather than other things. So that's another part of the philosophy. You see immediately PerGeos is more oriented to, let's say, a little bit more industrial use, rather than Avizo is more oriented to basically any generic use. There is no, Avizo doesn't guide you through a wizard, through a workflow, a path. It's a white blank area. You build your network, you do what you want. Avizo try to help you a little bit more into specific steps. And the other key point here, it will create for you visualization automatically. Because you cannot create yourself visualization, you see, there is no network here. So if you go to segmentation, you go into something that is not exactly like the segmentation editor, because there is no segmentation editor properly speaking. If you remember what is the segmentation editor, I open Avizo, is this one. So this one is the segmentation editor with a list of material. This is for Avizo. If I go to PerGeos, you still have the materials here. You have some capability visualization, but then the tools are here. They are modules, so they are. It's a little bit different. You can say I want to do like a brush or tool, etc. You will have to use tools like in any other processing step to do the segmentation. And everything you do here will be recorded, and it's not the case in Avizo. In Avizo, when you play with this, like let's say you select the pores, then you do watershed, blah, everything is inside here. The output will be going to the project, but how did you achieve the data is not recorded. In PerGeos, everything you do will be recorded. So if I go to the connected pore space and I go to the history of the object, I can find that I did the watershed, that I did the threshold, etc. So it's written in the history of the data. How did I achieve this? If I go to Avizo, there is no history per se. The labels are here, but I have no clue how this has been computed. Okay, so that's a major difference between the two tools. The user interface is different, and the way the action are tracked is different. Analysis, it's for the label analysis, and then you have explore. Explore, it's a little bit where you can do visualization in a little bit more freestyle mode. And just, yeah, so what else here? It's you can find, of course, if you are used to Avizo, you will find again the same modules. It's just the way they are organized that is different. But there are additional part of PerGeos that maybe we will speak about. And every panel can be hidden or displayed here. Okay, so it's yeah. So that's the overview. Let's go through the workflow. So again, I have a video. We're going to do roughly the same thing. Yeah. So let's start because I think I'm a little bit behind. Yeah, so so I start the video. Of course, at the beginning, you load the data, and you see immediately you get the data visualized. You have nothing to do, and with the right contrast. You don't have to specify anything. If you want, you can trim the contrast here. Anyway, so you have a viewer that could be, by default, the viewer tends to be 2D, but you can switch it in 3D. You can trim the contrast here, and this will be remembered for the entire user interface everywhere. So you do it in one place, and it will remain for all the processing. So we are not going to do pre-processing because it should be filtering the data and remove maybe noise. I'm not going to do it because I didn't do it in Avizo. I'm not going to do it in PerGeos either. So I go to segmentation, roughly the same. You get already a label material, I mean, something pre-cooked, and I change the name. So more or less same, you should be familiar. But I decided to call it marker to be more sure what I'm doing. So next I have to do roughly the same things I did before, doing some threshold. And you see the difference. I have a module that does thresholds in Avizo. If I go back to my Avizo, in the segmentation editor, I have a tool that does threshold. Okay, so it's a slightly different concept. So, but at the end of the day, you do similar things. You select the threshold you want. You do apply, you get it in the selection, and you add to the marker. And you do, again, the same things for the grain. Some range. Apply here. Plus, and here we are with our markers. And now I'm going to search. Yeah, so I choose the same color as the Avizo workflow to have something consistent. And I'm going to search for the watershed module here. Okay. So again, it's not a tool in the editor. It's a module that does computation. And similar, create gradient, apply, and and I can see since I'm not inside the segmentation editor because it doesn't exist, I see the data getting created. I always see my data. So you see I create the gradient. When I push here, I got the gradient. I have the markers. And now I will get a new object here because I push apply. This module will compute watershed and will bring me in a new data. Yeah, so now I have a clear vision. I have my markers, my gradient, and my watershed. And I will rename stuff around because I don't like the default names. And gradient, we can throw away. Yeah, I put the right, there are not any more markers. So another small difference, since I don't have my network with the ortho slice and color wash module, how do I visualize things? I already have these panels here to do visualization. So we know that people doing digital rock or porous media in general, they always want to put two data one on top of each other. It's super common. So you always have one and the other data, and you want always to overload them, let's say, display them. So you will all panels in PerGeos will always have these two guy here to show two data at the same time. Yeah, so you see what I did. I went to, for example, pre-process. On the left, I say I want to see my CT, a micro CT, sorry, here. And here I want to see my labels. Okay, so you have always this concept of display and compare, left and right. And if you click here, it's going to do the color wash. But you don't have to create the color wash, to create the ortho slice, everything it's already in place. So At the end, you will click a lot less in PerGeos to do the same things, but you will be a little bit more constrained on what you do. So it's a bit different approach in the user interface to go more straight to the workflow. So what I'm going to do here, I'm going to create, yeah, there are plenty of ways, but I need to keep only the pore space and throw away the grain. So I choose this way. I don't know, maybe I could have done differently. I duplicate the data and I throw away the grain. There are, instead of using the arithmetic, I did this way. I could have used arithmetic. Doesn't matter. It's just another way of doing the same thing. In all software, you always have many ways to do the same thing. Yeah, so I call it pore space because it's only storing the pore space. And maybe I should have used the arithmetic to be more comparable. So now what I want to do, same things. I want to compute porosity of the pore space and porosity of connected pore space. So I type porosity. A minor things, it's really detailed, but here the module is really called porosity. In Avizo, it's called volume, volume fraction. It's the same module, but since we know that we are in the domain of digital rock, we rename the module porosity because it's more intuitive for the end user. So we get the same computation. Then, yeah, connected porosity, connected pore space. It's the same things. I type connected, and in Avizo, I will get something called axis connectivity. That's a generic name. In PerGeos, I will get something called connected pore space because this is what you want to do. Again, it's just renaming the module in terms of user interface. But we think that makes the more intuitive for people in digital rock. So you have the two porosity computed. So I think I'm going to rename as usual. So I jump a little bit ahead, just renaming stuff. Okay, so next would be to separate the many click. Yes, separate. Again, I type separate. You may have seen it. You have separate object, but you have separate pore space. In Avizo, you have only separate objects. And then in Avizo, you choose separate object, then you have to change the mode, the algorithm to aggressive skeleton. And then you are good to go for separating pore space. In PerGeos, you just type separate pore space. We're going to do this additional step for you. So you get already in front of you a module called separate pore space that is already configured in the right way to separate pore space. Again, meaning a little bit less click. Okay, then the default is already pretty good. Okay, fast and repeatable. It's a tiny detail. So you get the computation. The computation at the end is the same. I mean, the two software in terms of image processing engine, they share the same platform. So you have seen, I got immediately the data visualized. I didn't have to choose, move the color wash, whatever. The last data that is computed is automatically put on screen because it's natural like that. It looks like a good default. And you can always say, okay, I want to see the separate pore space. You can always choose something else, but by default, you get the last one. If you want to do, yeah, that's another point. In the viewer of PerGeos, in this workroom, the viewer is most of the time looking at only 2D things. Yeah, you are in 3D space, but we always show mainly slices. because it's simpler for the end user. If you really want to do, let's say, fancy volume rendering things, you go to the Explore. And in the Explore, you are a little bit more like in Avizo. It's up to you to choose what do you want to visualize. So it's, this Explore workroom has been done explicitly to help people use to Avizo to choose their own visualization manually and not automatically like it's done in the rest of PerGeos. So we miss what? We need compute the size of each pore and do the distribution. So label analysis, same stuff. I have to create my own, let's say, custom group. That I think I can jump because this is not different. So I'm going to create a group with equivalent diameter and do apply, and I will get the table exactly like in Avizo. And then I have a distribution analysis module like in Avizo. There is a small difference. You see, I apply the module and I automatically get the chart. In Avizo, when you apply the distribution analysis, you get an object in the tree, but you don't see the chart. You have to right-click and ask to Avizo to render, visualize the same approach. Every time data comes in Avizo, you have to explicitly tell to Avizo how to visualize, with which technique. PerGeos automatically do it for you with the most proper method, we think. So it's a little bit more automated, PerGeos. And I save the project, and I think that's it. One more point. When I save the project, of course, I save all the data. In Avizo, you save the project, you save also the workflow, and it's very visible because you have the editor. And so how do I save just the workflow in PerGeos? You have a concept of recipe. So you can take any of this data, right-click on it, and say, please create the recipe. What's a recipe? It's a sequence of steps that has been used to reach this point. So if you right-click on the distribution, I think I have to go back. I click on, so I right-click here and I push create recipe, and automatically I get this list of steps. These are all the steps I did to compute the distribution. Okay, so I can save this and reuse it later on. The concept of recipe exists in Avizo as well. So you can do the same things on Avizo. Right-click on any data and say create recipe. But there is an important difference here. Anything I do in PerGeos can be, let's say, transformed in a recipe. In Avizo, it's not possible for everything, especially what you do in the segmentation editor. So to rephrase, PerGeos keep an history of every action you do, wherever you do it, in pre-process segmentation analysis, whatever. Avizo tried basically do the same, keep an history of everything you do, except inside the segmentation editor. Because the segmentation editor, it's a very manual tool. So it's not possible to really track every single things you do. So if you want to have a recipe in Avizo that does this sort of algorithm, you will have always to use modules. So you will have somehow to forget about using the segmentation editor. You will have to go all the time to build a network all the time if you want to have a full automated recipe. So why recipe is important? Because it's the way to redo the same things with other data. So it's for PerGeos, it's a cornerstone. It's an extremely important part of PerGeos to be able to redo again and again and again, because it's PerGeos is addressing people that are a little bit less in research, a little bit more in production. So this is why it's more automated and more the recipe is stronger concept. So you can save, of course, the recipe. You can document the recipe. I can show you how to do a recipe in Avizo as well. So don't get me wrong. Avizo can do recipe, but not if you go through the segmentation editor. So it's the only exception. So you have to know, if you want to create a recipe in Avizo, you have to think, okay, I'm going to do a workflow that doesn't use segmentation editor. So then I will be able to create a recipe at the end. In PerGeos, you don't care, you do what you want, and you will be able to save a recipe. Yeah, so that's it for the demo. So the next thing is, okay, in PerGeos, you can do a little bit more than just porosity and pore space distribution. So let's see the other step here in this workflow. How can I do it in Avizo? How can I do it in PerGeos? So up to here, fine. We have seen you can do it with both tools. Then you may want to do absolute permeability simulation. We have tools both in Avizo and in PerGeos to do absolute permeability, but they are not 100% the same tool. So I listed here. We have 3 methods to compute absolute permeability. One is through pore network modeling. So you can build a pore network model and then simulate. We have another one called finite volume. So this is going to simulate permeability through the voxel directly. You don't need to build any model. And finally, we have a third one that is lattice-Boltzmann. Again, this is simulating directly on the voxel. You don't need to build any mesh or any pore network. But this one is available in PerGeos. It's a choice that you have done many years ago when we create PerGeos. So that's the differences. Of course, each method has its own quality and disadvantage. So there are scientists that doesn't want at all to use pore network and other that likes it. So I'm not a petrophysicist, so I'm not going to tell you which one is better than the other one. I'm just a computer scientist. I'm telling you facts. This is different from that, and PerGeos and Avizo has these two methods and this one. They are additional license, just to be clear. So with the standard license of Avizo, you can do this path. And with the standard license of PerGeos, you can do this, what we have seen so far. If you want to do absolute permeability, you have to acquire an additional license that include a lot of simulators, not only absolute permeability. We can see that at the end. I have a slide with all the licensing and modules and extension, etc. So let's move on. Relative permeability. So relative permeability can be done only in PerGeos. There is nothing in Avizo to do relative permeability. And in PerGeos, this is done through pore network modeling. And we are going to see how. But the idea is the same. You segment the connected pore space, and then you ask to Avizo to build a pore network, and then to PerGeos to build a pore network, and then to compute relative permeability. So this is at the end what you will get, something like a pore network, etc. So I'm going to do it. The video. So yeah, load the data as usual. I also use a small variant. So I could redo exactly the same workflow to do to separate the pore space. Actually, I'm going to do it differently. I will use a recipe that is already embedded in PerGeos. So that's another point of PerGeos versus Avizo. Avizo has no recipe embedded. It starts without recipe. You can build your own. If you have knowledge in image processing, you create the workflow you like with the network editor. And then you say create recipe, you save it. Next time you start Avizo, you will have that recipe available in Avizo. But when you buy Avizo, it doesn't come with any recipe. If you buy PerGeos, it comes with, let's say, 10, 15 recipe documented for specific task. One of the recipes is the recipe to compute pore space on micro CT. So instead of going through the demo we have seen, I'm going to use the recipe. Okay. So you see, yeah, stop. You see, you have plenty of them. We will see some other like the EDS, BSE fusion. You have cubic porosity segmentation, core sample micro-CT, etc. So you have many of them. They are documented. So I choose the cubic porosity segmentation, and it's already long step. It's an advanced version of the watershed that I show you. It's with many more steps. Because you will see why there are more steps. So it starts. So first of all, you see the experience is I go to recipe, I choose my recipe, I select the input, and then I push play. You are in a wizard. You are driven. You are not creating any network yourself. You're just going step by step through something. You are guided, and you get documentation that tells you what to do. So here and there are breakpoints. You see this white dot? So some of the steps are fully automatic, and some steps require your attention. So when there is this, the software will stop automatically here, telling you to mark the pores, and you will be able to play with this threshold, and not the rest of the user interface. The rest of the user interface is almost locked because you are in a breakpoint inside the recipe. So you select the marker as you want. Also, I think in the demo I'm not going to do too much of it, but okay, you get the point. You can change. Why is that? Because the recipe is a good workflow, but for every data I got in, the threshold will be slightly different. If tomorrow I scan another Berea, this threshold is not going to be good, but the workflow is good. So this is why the recipe has breakpoints, to be a little bit flexible. So I choose my threshold. So sorry, the video. There is another. Okay, I have to go back. Yeah, maybe even more. Yeah, so there is an additional step we didn't do in my simple demo. We may want to add some markers for the pore space in the thin throat. There are some very thin throat here, like this one. If you use a threshold, you are not going to catch them. But there is another image processing module that is called TOPAT that can help you to identify this threshold. This throat. And so this is why in the recipe there is this additional step. It's still to put markers in the pore space, but with in additional you can add TOPAT. And TOPAT, you see what it does. I'm not going to explain you how TOPAT works, but the key point is that you are going to be able to identify a little more markers. But the grain is the same. You just select. Is going on. Is going to start watershed for you, so you will not have to push create shader, blah blah blah. Create gradient. It's totally automated, and we'll let the option at the end to have a final top at, because maybe the watershed has killed some of this thin throat, and we want to keep them. So there is an additional top at that you could, if you want, add more thin throat to the. So you see what? Yeah. So this, I think it's an important point. This is the automated detection of pore space. You see this very thin throat has not been able to be detected. But since you have this final top at, you can get it back. So what does it mean? If you go back to Avizo, you may want to create a workflow like this one. If let's suppose you don't want to use PerGeos, but you want this workflow, you will have to do a longer sequence of steps in which you will add a top at. So you can mimic this behavior in Avizo yourself. but you will have to know how to do it, and you will have to do it. So anyway, now we have our yeah, you see, since we have been through a recipe, all the things like the markers, the gradient, they have been thrown away by the software. You don't need to do it yourself. The recipe focus on giving you the labels of the pore space. So now we are kind of back to the same point as we were with Avizo. We have a pore space, so we can do porosity, we can do whatever, but our goal here is to get relative permeability. Okay, so first you keep only the connected pore space, because it's useless for permeability to have the non-connected pore space. So this step is the same, and then we want to do two-phase flow. Relative permeability, we need to first of all build a pore network model. So there is a model called pore network model extraction. I select pore-based two-phase flow, and well, this is one tiny detail. I prefer to rename the recipe. Didn't change the name of the pore space into pore space. It's still called inside. I do it manually, but it could be done in the recipe. The person that developed the recipe forgot to do it in a way. So I think I will go back to my pore network model extraction. Yeah. So I say the pores are this one. Yeah. A detail explaining the two-phase flow theory and so on is very long. So I'm going to skip this. But what you can do, you can also segment a microporous phase if you are able to do that, and say to the pore network model extraction that you have a microporous phase, and you can give the porosity of the microporous phase. So this will be taken into account if you do the pore network model relative permeability. Sorry, where we are behind. Yeah, so I think this is computing. I recorded also the computing part, so you get an idea how long it takes. And this one I didn't accelerate it, I think. No, I don't think so. So it's doing the computation. It takes a while. It's still a small data set, so it's not very long. In real life, I would say, when you have like a huge micro CT, you will need a quite powerful workstation. This process is done using all the core of your machine. So it's a multi-process computation. And here we are. What you get out is a pore network with a lot of properties on each pore and each throat. And you automatically get some sort of visualization that you may improve. This is a little bit not very clear. So you see you have a pore network viewer in which you can select how to color the pores, how to color the throat, how to scale the pore, how to scale the throat. So you can trim a little bit the visualization to make it more. You see how many properties we have for every pore and throat. Okay. Yeah, so I think I played a little bit with that to reach something that I like. So I can see the size of pore, it's relative to, I think I play too much with so I can skip that. So anyway, this is the pore network. Avizo cannot compute this specific pore network. It's a specific pore network for two-phase flow simulation. In Avizo, you have a pore network extraction module that can only do absolute permeability and pore network statistics. So it will look the same in the sense that it's going to be pore and sticks, ball and sticks, but you have not the same property on the pore and throat, and the algorithm to find the pore network is different as well. So basically you build the pore network to the simulation, and the way you build the pore network depends on what you want to simulate. and you have different algorithms to do the pore network. So yeah, this is just to co-visualize the pore network with the segmentation. I think we can jump forward, because the next step would be to compute. Yeah, so you have two-phase flow simulation. I show you all the property quickly in the video. So here we are. So this module is very complex because it does two-phase flow simulation, this complex task. I didn't go through all the parameter. You can do the primary drainage water flow in second. Everything is optional. You can decide to do only part of this experiments, only one of them or three of them, and you can decide the direction of injection, etc. So it's not the goal today to go into this details, because it's you do apply the computation by itself. It's quite fast, because that's the concept of pore network, right? If you want, you can do lattice Boltzmann two-phase flow. It's going to be very slow, and it's going to be on each voxel. So the pore network model, say I build the pore network, takes a while, and then I can simulate through pore network faster. And so you can change the input and out the parameters of the simulation and obtain multiple simulation. Anyway, so the pore network model will produce tables like that, and it will render automatically the chart, so all the curve. I'm not a petrophysicist, as I said, so I will not comment too much on this curve, but you get the idea. So the simulation will produce all the data and will render it, and you can of course save it, and it will give you in the tables plenty of information, like a lot of things will go out of the simulation. So all the input, so you can save this as an Excel file. You will have all the information about the input and the output in the same Excel file with multiple tabs. Like, of course, you will get the absolute permeability, the connected porosity, the formation factor, blah, blah. You can read them. So this is a quite powerful simulator indeed, and it's PerGeos only, because it makes sense. PerGeos is born for digital rock specifically, so this is why this simulator is only in PerGeos. And I saved the project, and that's it. I think it's finished. Okay, so that was the demo about two-phase flow. I think I go on this second topic. So we finish PerGeos about I think micro CT. I know that in the network, Excite network, there are people with SEM, and PerGeos and Avizo can handle, of course, as well 2D images and very large 2D images. I thought it would be nice to have some example on that. So this is a data set that have been gotten from this university. I think they are in Australia, if I remember well. So the idea is, can I do anything that use multimodality, like a BSE-EDS? What can I do if I have both of them? What analysis can I do? Okay, you can guess. If you have only the 2D grayscale, we can go through the pore size distribution workflow or the grain size distribution workflow, exactly like with micro CT. You can threshold, pore and grain, watershed, split them, and do exact same workflow will work. If you have in addition this information, that is the mineral, then you can say, okay, maybe you can easily imagine that you can do, I don't know, pore size distribution only of, grain size distribution only of quartz. That's quite obvious. There is one tiny problem, is that the resolution of the two is not the same. And sometimes, depending on which machine you use, they may not be aligned perfectly. It depends. It depends which acquisition device you use. So the goal, ideally, what we would like to have is at the end something like that, in which you have each grain assigned to one dominant mineral. So there in PerGeos there is a recipe for that. So I'm going to show you the video on how. So I have a full project with all the analysis. Try to go quick because I think it's a bit long. So this is your input BSE image, and this is your EDS image. And I will probably activate color wash and then choose the right color map to see the color of minerals. And as you probably know, they're not same resolution. This is what you get usually, something like that. So it's not so obvious to say what's the mineral of each grain, because probably they are a mix of minerals. But if you want to do some statistics, like a grain size distribution of quartz, you may decide to say, okay, I can assign to this grain a single mineral, the most important, the most relevant, the most present. So how do I do that? Well, there is a recipe in PerGeos to do that. So I go to the recipe, and it's called Fusion EDS BSE. I give the EDS, and I play the recipe, and you see the steps. So well, I'm not going to comment. It's a recipe. Yeah, why I accelerate the video? Because this data set is quite big. Maybe I go back to the, it's 16,000 by 16,000, okay? So it's a mosaic actually in the acquisition. And with PerGeos, there is no limit. You can have a really huge data. So let's go back to the video. So I accelerated the workflow because some steps are slow. I mean, they are long to take because of the size of the image, especially the separate part. So, so 2D can be time-consuming. It's not only 3D, and there are some steps in this workflow that are longer than others. For the demo purpose, I accelerate. Yeah, so for example, registering the two images, if they're not very well aligned, it takes time. To split them takes time. So what's the output of this recipe? Something like that. We call it majority. Somehow each grain has been assigned to the mineral that is dominant in the grain. So it means we have been able to split them and decide what is the most dominant one. Okay, so from now on, you have plenty of opportunity to do analysis, right? It's a major step, and the resolution is the same. Actually, that's another thing. Maybe I didn't tell you. It's clear here. You see the EDS now. It's at the same resolution of the BS. So the two acquisition are upscaled at the same resolution. So because we have chosen to select the most relevant mineral in the grain, we can do this upscale. It's a choice. For this specific workflow, it's a good choice. So if I now I can do, for example, a simple things like show me only the quartz, and I will get the resolution of the grayscale image, the quartz on the resolution of the scale of the grayscale. So that's pretty useful. So what can we do? For example, we can compute the size of each grain and do a sieve analysis. So you color them, you split them in 3 classes of size and color them like that. By the way, this could be done also with microCT. Of course, once you have the size of each of them, you can do plenty of things. You can filter. Let's say, show me only I don't know, the grain that are smaller than a given size. You can do plenty of things. Again, this could be done also with microCT, FIBSEM, anything. You can, of course, see the large one. And that's another one. You can only select the elongated one. So again, you remember label analysis has 1,000 more measurements. once you have been able to separate each grain, then you can apply the measure you want. For example, the ratio between width and length. And then you can put a filter and say, show me only the grain where the ratio is bigger than that. So you have all sort of. So this is true in 2D, 3D. So another things, you can focus on mineral 163, that is maybe, I don't know, quartz or whatever, and do the same analysis, but specifically for that mineral. So you will get, the pore size, the grain size distribution of quartz. I'm going to jump. It's the same exact workflow. You do PSD. If you follow the presentation, you know but it's restricted to this mineral. Yeah, so same, the usual things we saw, but for a specific mineral. So I hope you appreciate this. Yeah, these are slides showing things I already showed you in the video, so I don't think we need to go here. We can skip. Yeah, another workflow I've seen is there is some company that has even a third, let's say, sensor. It's a cathodoluminescence sensor that highlights more the structure. So you can imagine to achieve, for example, you could try to identify the quartz overgrowth. How do you do that? You have the BSE, you segment by thresholding the grains, then you select only the quartz because you have the BSE, and then you go and you to the CL and you find you threshold the CL. So basically you will be able to say, inside my quartz grain, I want to see only the portion in which the surface structure is like that. So I know it's an overgrowth. So you will be able to quantify the percentage of overgrowth in the quartz versus the part that is not overgrowing. So these sort of things, the more information you have, the more you can correlatively do analysis. There is no limit. You can. And if you have multiple machines, usually the acquisition is not aligned, but we can align them. So that's pretty interesting. Last one. Let's say the workflow I show you up to here, most of them can be replicated in Avizo, but you have to know the recipe. In PerGeos, you don't need to know the recipe, it's already there. But theoretically speaking, I think if you are good in image processing, I think you can redo this workflow. And last one, I think, if I remember well, yeah, so it's my slide before the next break, I think. We have in PerGeos only, you can do processing of something that is bigger than your RAM. So that's a specific feature of PerGeos. For example, here we have got a 56,000 by 86,000 thin section image. And we have been able to basically do a pore size distribution or a grain size distribution. Some steps can, so this is not possible in memory because the data set is too big. So you prepare a recipe, what you do, you select a region, you prepare a recipe that does the work. And then you say to PerGeos, apply this recipe on the entire data set by slab, by block. And of course, we know how to merge the output of the blocks, because at the joint between the two blocks, you will have to do some work. And then you go through the standard label analysis workflow, you know already. We have a video of this in action. So I put a link here. You will get this slide with the link. So it's a specific feature of PerGeos. Although we always suggest to buy more RAM. So to do this out of RAM, it's nice, but it's going to take maybe 3-4 times more than what you expect, because you have to go through disk and do it offline on disk. it's going to be probably a better idea to buy more RAM on the machine. The RAM is not so expensive nowadays. So when a customer comes to me, say, I have not enough RAM to do this workflow, I can answer, okay, PerGeos can do, but I always say consider to buy more RAM, because at the end, you will be happier with more RAM, I think. Well, anyway, so that's it. I think we are here. So it's about how to extend Avizo and PerGeos somehow. It's a pillar of Avizo, I would say, and PerGeos as well. But for sure, this is coming from Avizo. You understand, Avizo is very much used in research. So in research, you always want to do things that nobody think about before. So being able to extend the software with something new, with your science, with additional blocks, it's a strong demand. So recently, Python has been the most used language to do that, and so we will see how to do it. So it's a mini tutorial I prepared. Again, it's a video because I think it's going to be fun. I thought doing it manually, but it's going to be too long. So let's go straight away. So this is my plan to show you how to use Python in the console of Avizo, and then how to create some extension of Avizo, and you have plenty of other resources. So so I start the video. Yeah, so the idea is that you start with you're already in a project with data and so on, and you want to start experimenting Python. It's the first time, you never saw it. So in Avizo, you know Python, but what you probably miss is how do I exchange data between Python libraries and Avizo objects. So if you come here doing Python stuff, is because you already think that you have some science, some code, some idea that could be done better in Python. For example, you want to do a segmentation by Python. You know some algorithm for microCT that you think it's the best one. And so what you will need is to be able to collect the matrix of grayscale value that is inside this microCT, put it into NumPy, probably array, then start your workflow in NumPy, in scikit, whatever you want to use. And when it's finished, you want to put it back into an object that is a segmentation of Avizo. That's a very common usage. Other people just do image filtering. So you start from a grayscale, you output a grayscale. But the segmentation one, it's a pretty common. So I try to go there. But at the beginning, you want to understand, to experiment. So what you do, you go to the Python console. I don't know if it was clear. How do they? You click on this small icon here. You get on the Tcl console by default. You click on Python console, and you get here. And here you are in Avizo, but you can write Python code. Okay, so it's an integrated interpreter environment inside Avizo, where you can experiment a little bit. So you can import NumPy as an NP, standard code. And then, so what I want to do is to get the data that are inside this object into a NumPy array. So first I need to get a sort of handle, a Python handle on this object. How do I do that? I click on the object and I go to the console and I hit tab. If I hit tab, Avizo will write for me the code, the Python code, to get an handle to this guy. Of course, I can write it myself, but I'm lazy, so I prefer to click, go here and hit tab. I will get this. So what is this? Is I'm asking to the project, give me a handle to this data, okay? And I need to put it somewhere in a Python object, so I will do something like this. Yeah, so this is the code you have to write. You can write it completely by hand or get help by the tab. Anyway, so what is this? Now Berea is a Python object that represents an handle to this data. And now I will ask to this Berea object, give me the NumPy array of your matrix. So I can start to look at Berea like this because it's an object, so I can. So I will start to create an input array equal Berea dot get array. So you see. So now I have a NumPy array. Maybe it's too quick. Let's go back. So I create an input array object, and I say input array equal Berea dot get array, and finally I have yeah, it's a bit too fast. I have my NumPy array that contains the matrix with the right shape of this volume. And now I'm free to do whatever I want in NumPy or any other Python library. And then I can push back the data into, or I push it back in the same object. And normally this is not what you do. Usually you create a second object and you put the output there. So you can query the min and max of your input arrays, standard things you do with NumPy. Fine. So my goal is to do a sort of simple thresholding between min and max. So I start to create a min object and max. Let's say, yeah, this is the pore space roughly, right? So it's between the minimum and 11,000 we have seen. So now I create an output array, a NumPy output array with a Boolean expression. So I will say if the input is bigger than the minimum threshold and is smaller than the maximum threshold. So this is my Boolean array. I change the type to be compatible with the labels of Avizo. It's a NumPy unsigned integer 8-bit. Okay, it's a bit of computer science. So now I have, maybe I stop here. So I have now in this output array a binary segmentation of my input, right? So I have 1 when the voxel is in the range, and I have 0 when the object is outside the range. So it's, of course, it's a silly, basic, stupid segmentation, but it's to give you an idea. This code could have been extremely complicated with your own, I don't know, machine learning code to do segmentation. Anyway, so now I have to create an object in the tree, in the project of the right type to host this segmentation. So this is what I did. I say to the project, please create what? And I have to write down the class, the right name of the class to host a label field. Okay, from the documentation, I know this is the right name of the class. So it's a uniform label field 3. And as soon as I say result equal blah, 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 enter, I get an object in the project. Okay, so you see by Python, I can create object in the tree. To let you know completely, you can create, destroy, connect. You can create the network by Python completely. So I could even have loaded the data from Python. But okay, this is still an empty object. You see, there is it's just a shell. The size is 2 by 2 by 1. There is no data. The size in the physical size is completely wrong. So I have to do something to populate this label field. But first, I will have to put the right bounding box, and then I will have to feed this output array here into this object. So we are going to do it. So first of all, I change the bounding box, if I remember well. No, I decide first to set the data. Okay, set array. You see, there is now a star because the data has been modified, but still I don't see anything, so something more has to be done. The data are now into the object, but still the object has not reacted in a way to this. So what I do, I change the bounding box as well. And which bounding box I use, but the same of the input, because it's a segmentation. So they have the same bounding box. Still, you may notice I have done things, but nothing has changed here. It's a default behavior of Avizo. You have to explicitly call a method called fire to trigger updates. Okay. Usually this happens for you automatically when you are not in Python. So after I say fire, finally, maybe I can go back here. My object is really populated correctly. I have the right bounding box, the right data, the right preview. So I could save this into label Avizo format, and that's it. I've done my segmentation automatically in Python. So I think now it's just going on with connecting to visualize the data, basically. So I think with color wash, I can jump. Yeah. By the way, I could have done this color wash, ortho slice, etc. in Python. Okay, so it is possible. I told you to create object, not only data. You can create computation module, everything. So next is a little bit complex. It's a small jump because we have not much time. So it's fine to play in the console, but what you really want is to have a new module of Avizo that does this kind of work for you. So what you want here, you just play to understand, but what you want to do is to be able to have something that you right click on your grayscale, you get a new module written in Python that does this kind of things. And when you hit apply, it will give you the label field. Okay, so how to go from the tentative code I wrote here into a proper module? Well, we can see it a bit quick. So you will have to write a PyScroll file. So the extension is important. It's a PyScroll. It's a proprietary extension of Avizo. It means a script written in Python. And you will have to respect some syntax. It's documented, of course. But to make it short, you need to create a class that derive from PyScript object, and you will have to implement 3 methods: init, update, and compute. The init is just creating somehow the user interface of the module and giving some type on the input. So you are creating the ports and the user interface that goes with it. Okay, so like every other module in Avizo, every other module of Avizo will do the same, even the one that we write. They start initializing themselves. They have a method to update. So if somebody touch some port here, or if somebody connect a new output, the module usually update itself. So you have to think about what happens if somebody connect an input to my module. You will have to do something. And then compute, if the person push apply, we will go through compute. So you have to, of course, you have to read the documentation and understand all of that. But in a quick demo tutorial, I'm telling you. So you see the 3 important methods you need to create. I can let you know where are examples like this one. Okay, don't be scared. So let's say I create this script because I read the documentation. Somebody sent me this script anyway. So I learn how to do this in somehow in a training. We do training, of course, to learn how to do this. But you have plenty of resources I will show you to learn yourself. You're not obliged to follow a training. Maybe important things. I create some input port. Why? Because I want to have a module, a module here that give me a range. And then in the user interface, so maybe I spoil a little bit. What I want to get is something like this, a module that can stay in the network, that has as input a grayscale image, and I want a range port like this, where I can play and then do apply and get output the segmentation inside this range. It's a super basic concept, but at least I think you get the point. So how do I do that? I write this Python code, I save it in a PyScroll file, and to start experimenting, I can drag and drop the PyScroll file into my network, okay, like that. So Avizo, what will do Avizo? Since it's a call PyScroll, it understands immediately that it's a script. It will read it, interpret the code, and if the code is correct, you will get the module instantiated. If there is a mistake in the code, it's very common at the beginning when you start writing it, you will get error messages popping up telling you the line number, blah, 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 I saw this error. So you will have to go back to your text editor, modify. If you don't know exactly the syntax of something, you play in the console. So console is is the place where you can do really your first steps. And when the code looks nice, you copy it into the PyScroll. And the PyScroll, of course, should be more generic than your code here, but that's the idea. So let's suppose you write the right code, you get this module, and basically you're done, because what happens is that I'm showing you again what's here. So you have, I try to comment a little bit the code. It starts saying self data visible equal true. Data is the input. And I change the name into input grayscale image. So this is why I have this label here. And I say I accept as input HX uniform scalar field 3. What does it mean? I accept as input only basically cubes of grayscale images. Okay. So I can restrict the type of data accepted in the input. And then I say I create a port range slider and I call it threshold. And so suddenly you will get this guy here. So I'm creating the user interface of my custom module in Python. And I also set up min and max. By default, I have no clue about the min and max of the input. So I put some default value. But this need to be updated when somebody connect the input data here. I will have to update this input, and this is the job of update. Okay, so this is just to initialize the module. So when I drag and drop my PyScroll here, Avizo will just go through this. Then, as soon as somebody connect some input, then Avizo will go through the update. And this is where the magic happens. I will ask the NumPy array, compute the min and max, and set up the threshold min and max to the right value. So I think I can do it. Jump a little bit. Yeah, so I connect and magically, let's say not magically, it's the code doing it. The code is updating min and max. So this is what the end user expects. And then, yeah, so this was a previous data set. Yeah, I don't need any more my console because now I'm really working with the file, with the script. So what happens if I move any of this? And then I do apply. Everything I move here is going just to be through the update. If I hit apply, is going to be through the compute. And the compute really create an additional object with the code I showed you before. So it's going to create a label field, do the threshold things, store the output array, etc. And I don't know if you know about auto refresh. It's a feature in all Avizo module. You can ask to Avizo that to be in modules to be in auto refresh mode, meaning every time I touch anything here, apply is done automatically. So but that's an option. It's an Avizo standard thing. So I can create a color wash, connect to the output, see the yeah. So I'm just doing nothing related to Python anymore. This is standard Avizo feature. But since I'm in auto refresh mode, everything I move this, the Python code will continuously be executed, and so I get the output continuously updated, like any native Avizo module. Okay. So I say Avizo, but you get, I guess the point could be PerGeos. So the Python basically, when we speak about Python, Avizo and PerGeos are 100% the same. One more point. How can I really integrate this module into Avizo? Because now it's kind of integrated. You know, I have to find the PyScroll on the disk, drag and drop. I don't like it. I want my idea would be to really be able to start Avizo as usual, like I do every day. And when I got a grayscale, I want to be able to do right click on it and find a new module that I create myself that is called simple threshold and do this work. So I want to really have a proper integration of this module into my Avizo. How do I do that? There is an additional step. We need to create another file that explains to Avizo what this PyScroll is going to do. So this is a little bit technical. We are not obliged to really go through it. It's documented as usual, but it's a syntax you have to check. In a way, it's a sort of meta file that is telling you this is a module called like that. This is the type of data it accepts. It's written in Python and is going to be in the category Xtra image segmentation binarization, and the file code is here. Okay, well, it's kind of intuitive. So these two guys goes together. You need to keep them always together, and you will see. So at the moment, these files are in my own hard disk somewhere, so Avizo cannot find it. So I have to put this in the right place. So then when Avizo starts, it's going to read this and these two files. So I have to put it in a special place that will be read by Avizo at startup. And so they will be really integrated in Avizo. So where do I put it? I will put them into something called, so I'm going a little bit through the help. Maybe I can do it with the real Avizo instead of the video. So if I have a real Avizo running like this one, how do I find the information about Python and so on? I have a menu, Python. Python, okay, you can start first from the help, I think. So like examples. Oh, here you get plenty of examples, so maybe it's better to go home. So automating, customizing, extending. What I'm doing is extending. So I click extending, Python scripting, and you start to see you have a tutorial of Python, you have plenty of things. I want to do a script object. This is what I'm doing. And you see you get, okay, you have to respect this init, update, compute. You can create port. So everything I'm telling you is documented, of course. And then it will tell you have to create a resource file, the .rc. I show you with these tags. And that's it. So everything I tell you, it's in the documentation. So normally, so let's continue the video. Yeah, so I think I did exactly the same thing. So we can jump. Then the last final step, a little bit tricky. I have to copy this in another directory because otherwise Avizo will not do it. So I copy. Where do I put it? I put it in a directory that is called Avizo local. It's what's this Avizo local? It's a directory that you can create yourself. An empty by default you create an empty directory, and then you have to put some structure in it. We can skip a little bit of detail, but let's say it's documented as well. if you create an Avizo local directory with the right structure and you instruct Avizo to go and look into this directory, you can inject into this directory everything to extend Avizo. Okay? It could be TCL, C++, Python, plenty of things. So the Avizo local concept is every user can have his own Avizo local directory with extension to Avizo. Okay. In the case of Python, it's going to be inside share Python script objects. And you need to respect the right syntax, the right naming. So there are rules, of course, otherwise it will not work. But if you do it properly, you put the file in the right place with the right syntax and so on and so forth. Yeah, so if you restart Avizo from scratch, you will get this module integrated. Okay? So that's I restarted Avizo. Jump. So I reload my project, and if I right click, this one we can throw it away because we want to use the new module I wrote. If I right click here, I will get an extra category with my custom module. And here we are. Now it's properly integrated into Avizo. Okay. So this is quite powerful if you understand the. I mean, I'm a computer scientist. For me, it's really something amazing because you can have your own science into your own custom module while keeping Avizo. And if you know Python well, you got the point. You can create new modules. You can create workflow. Everything could be written in Python, basically. So if you get some students with this knowledge, it really open up a lot of possibility to extend Avizo. And last but not least, we have this. So I go it. So we push the concept of extending Avizo a lot more further. So this is Chrome, my Chrome. So you will get this address here. Maybe we can copy it in the chat. We decided to create a portal where we can add add-on to Avizo. Okay? So since Avizo, PerGeos, and Amira, they are extensible by anyone, we thought could be a good idea to have resources online for free that you can grab and add to your own installation. So how does it work? You have this portal and you have a lot of stuff here. Some of these are just, let's say, a video tutorial, for example, a demo, or there is somebody showing you how to do things. Some are really Python module. So you can click, you get a description, you have somebody explaining you what it does, and you can download it. And if you download it, you will get a PyScript, a PyScroll, etc. that you can put in your installation. There is always written on which version it works. Sometimes you can port it to different version. We tried, of course, to keep it updated with the last one. And you can also filter by product. So if you want specific extension for PerGeos, you select PerGeos. And here, of course, you can expect something a little bit more specific to a Digital Rock. But even if you go to Avizo and Amira, indeed, you will have a lot of things that could be useful for Digital Rock domain. But they're not specific to this. They're just for any material. Okay. And these are just the Python, okay? If I remove Python, if I say, let me show everything, it's a lot. You see 7 pages, every page there is probably 20 or 30 of things. So I strongly suggest you find the time to go through them. Some are probably not applying to your domain, like this one, it's specific to get membrane. So maybe it doesn't completely apply to your domain, but And some are 2D, some are 3D. You have plenty of things. So this is a really wonderful resource where to look. So yeah, I put it also on the video. Yeah, another resource online, very useful, the Learning Center. So if you type YouTube Learning Center Avizo, or you can type PerGeos, you will land into, for Avizo, you will land here. So you have plenty of videos that show you how to do things. Like, how do I do a multi-phase segmentation watershed? How do this, how do that? They are more nice than reading the documentation, basically. This one is important. You get, how do I set up to be able to extend Avizo and PerGeos? So you need this special directory. You have to tell Avizo and PerGeos where is their special directory. PerGeos Learning Center, same things. You get a lot of stuff we didn't speak about yet. Plenty of things. So I strongly suggest you to look at this. The Xtra library. I will, at the end of the this tutorial, I will create a page with all these links, so you will get all these pointers. Okay. So yeah, so you get the point. You have everything online. So indeed, yeah, there is one specific to Python that I really like. So it's done by Trevor, one of our product application engineers. So it's a little bit old. You see the interface, it's still older, but it shows you how to explore, how to do things. So you should look at this video. Is it where? It's in the, I think it's in the Learning Center of Avizo, and it's written Python in the text. So there are plenty of them, but there is one specific to Python. I think it's yeah. Oh, you have to Google it. You will find it. Yeah. So this one is pretty nice. It does roughly what I did, with a little bit different. So it's complementary to what I did. But yeah. So so next, I don't know how late I am.
We were supposed to have a break like 5 minutes ago, but
Okay.
I suggest you to
Finish
start
this
with
one.
the machine learning. Yeah, because it's not.
So
yeah, if everyone is okay with it, we're gonna start with the deep learning segmentation, and afterwards, Fede will be showing us the difference between Avizo and PerGeos.
Yeah.
And then we're gonna move on into the open Q&A session.
Okay, so I try to speed up a little bit.
Oh, it's okay. You're on time.
Python. So a lot of people wants to do Python to do machine learning or deep learning, right? So because you have so many resources. So we decided to create a simple example in the Xtra that shows you how to do to use scikit. So let's go. And so where did I found all this? The module, it's on the Xtra. Okay, so I show you here. It's the link. If you download this example, you will. It's for PerGeos. The code can be reused in Avizo, I think, with maybe few modification. So I decided to show you the power of this module on FibSem shale rock. To do something that usually is quite tricky is to segment the three phases of shale, so the grain, the pore space, and the clay. Okay, so it's typically a bit tricky to do that. So with machine learning and deep learning, you may have more success. So just to be back, how the model works, it's a sort of proof of concept, right? Is provided as is free. So you should not expect is the perfect final tool to do to do segmentation of FibSem, but it's a good starting point. So the idea is that it's a supervised machine learning. So you will have to provide to the module some segmentation. So you will have to help the machine learning, basically. The segmentation will learn and use a random forest classifier and then try to predict. You give the labels only on the first slice, and then the prediction will predict on all the slices. Okay. So how it looks like? It's a PyScroll. So this is my input. So I have 40 slices of 200 by roughly 200. It's a FibSem shell acquisition. Yeah, so, and you have pourebacks, you have all the usual problem with FibSem. So what I did, I just I segment manually only on the first slice, the slice 0, you see. I say this with the paint. I paint the grain, I paint some clay, and I paint some pores. Not much, actually, to be honest. I mean, it's a bit challenging, you see. But this is the input. This is my ground truth. Yeah, so I think we can jump. And then I'm going to use the module. So there is no .rc in this case. So I just drag and drop the script. So I drag and drop the script. The script has only two input: the label with my ground truth and the grayscale image that I want to predict. So there is not much else. And then I hit apply, and the module will execute the Python code. That is a scikit code mainly. I speed up the execution because it takes a while. You can imagine it's a quite large image. So the output of this Python script is a segmentation that has as many classes as the input you give, and is done automatically by Python. So this is just to let you appreciate what you could do with Python. You can really extend the Avizo. I know plenty of people that has Avizo and do this outside Avizo. So they say, yeah, Avizo, I use it just for visualization, and then I do my processing with, I don't know, ImageJ, Python outside. And for us, we don't really understand why people don't integrate everything like that, because it's going to be a lot more easy for you to work with tool integrated into Avizo. So you can, this is PerGeos, but in Avizo you will be able to have your own workflow. And at a certain point you stop, you have one of the block, it's your own custom Python code with your own capability of doing segmentation. So you will be able to automate the workflow, to repeat it with many other data sets. So if you integrate your own code, then you will use the facilities of Avizo. So you will really speed up the way you work. So this is the result that is quite good. Maybe it's not perfect, the code is not perfect, the code, but you can get this code for free. So, but I think it's a nice place where to start if you want to do this sort of things. So I go next. Yeah, so this is the library. So why you are able to use Python in Avizo and PerGeos? Because we put this environment in place. So you have all this library already loaded into Avizo, and you can customize this environment. So it's in the documentation. If you want another version of scikit, or if you want to add more modules, etc., you can do it. Usually it's not so common, but it happens. And you have actually two environments. One is the vanilla Python, is this one on the left. And you have an additional one that we call deep learning. By default, we don't install all this one, but you can decide to add them through the interface. So by default, you get an Avizo with Python interface, plus you can click and say, I want to download also the deep learning environment. You will get all this stuff in addition. So if you think to code deep learning stuff, you can probably do it.
Well, all right then. So we are at the final stage of the workshop. So Avizo versus PerGeos, and a Q&A session where everyone will be able to ask questions. So Fede.
Okay, so let's move forward. So, well, the natural continuation is how do I do deep learning segmentation? Okay. Somehow you got already one possible answer is you write your Python code yourself, but this is not super accessible to everyone. So we thought that is something we should develop in the product to democratize a little bit deep learning. So we have done some work on it. Still, deep learning require a data scientist, I think. So you need to know about deep learning. We have done the tool to let you do deep learning without coding anything. But still, if you don't know anything about data science, then you will be a little bit in trouble, I think, to do deep learning. We do it for you if you want, but it's a service. So we, yeah, with especially with the industrial companies, we do deep learning for them. For university, we teach how to do it, but we don't teach the data science. We just teach how to use Avizo or PerGeos. Okay, so to summarize, deep learning is about training and prediction. To make it simple, of course, the difficult part is training. So today we have two modules in Avizo and PerGeos and Amira, of course. It's the same modules. There is no difference between PerGeos and Avizo. It's the same platform. So you don't need any special license to use it. It's integrated in the core of the licensing. You need to have installed, let's say, the deep learning environment. How does it work? You start Avizo or PerGeos and you go to Python environment. By default, you will have this embedded Python. You will have to do create new environment and then do install and then type a name like deep learning. I suggest to put the version where you are, because this package may eventually in the future change. So my suggestion is to call it, I don't know, 2021.2. I will not do it, but then you do OK. It's going to download the Python package, the additional Python package necessary for deep learning. I did it already, of course, so I have them available. You see here. So I have actually two different versions and the embedded one. So you will be guided at how to do this, but yeah. So if you want to really do deep learning yourself after this tutorial, you will have to follow this. So let's go because we are a bit late. This module we have done are actually very complex Python module, but for you they are just let's say two modules integrated in Avizo and PerGeos. The usual strategy for deep learning is to do it in two steps. Most of the time, this is what we suggest. So first step, you do a quick training. And then when this is done, you continue with the more accurate training. It takes usually a lot of time, a lot of resources. So you need a specialized machine to do that. You need a machine with a good GPU. Especially the RAM is not really an important factor. What's important is the GPU, because everything happens in GPU. The biggest RAM, but the biggest GPU memory you have, the better it is, because this is going to be a bottleneck. We typically say you need at least 8 GB on a real data set in the RAM, or not in the RAM, sorry, in the GPU memory. But if you have more, it's better. So let's go through a video that shows, of course, it's a short video with a simple example. Real life, it's a bit more complicated, but if you want to understand the concept, I did it in PerGeos, but it doesn't matter. It's the same in Avizo PerGeos. So what's the tutorial about is try to segment the Berea again. So you will be able to do this yourself. This is why I choose this data. So I will learn from a portion of the segment. So I will only select a portion of this my segmentation, and I will use it to learn. And then I will ask, predict on the entire data. In real life, what you have is that you have probably many data sets, and you will learn from few of them, and then you will predict on others, okay? Or you have a huge micro CT, like with, I don't know, 2,000, 3,000 slices. You will segment part of it manually, and then you will say, okay, now try to learn from this manual segmentation I've done and predict on the entire data. That's the standard scenario. Here, to make it simple, I take, so I have my Berea, I have a region of interest that is this portion, and I have the labels only on this region of interest. And I will try to, let's say, predict. So I jump a little bit. So you see where I have the segmentation is just the bottom part. So I instantiate this deep learning training module that has a lot of parameters because deep learning is not simple. The first input is the grayscale. The second one is the ground truth. It's the segmentation I did myself that I know it's correct. Be sure that is correct. You have to, if the ground truth is not good, you will never succeed to do good deep learning. So be sure that you have a good ground truth. And then you have plenty of options. I'm not going to explain all of them. It's not possible, too long. Let's say first here you select you give a name to the first training. You call it first training, and you have to select something. And this is maybe a parameter. You will run only few epoch. It means deep learning is a converging process in principle. You learn from one step, you go to the next step from the previous one, etc., etc. If everything is well done, you will see the precision going better and better, and so you know that you are on a good step. If not, it's going to diverge, and then you have to stop and change something. So you have plenty of parameters, but the tricky one, the most important one is how many epoch and what's the rate, at which speed you want to go in the training. If you go too fast, you may lose the good path, let's say, to the convergency. If you go too slow, you're going to converge probably, but it's going to take a lot of time. So it's an art, it's a small art to be able to set up this parameter. We teach this in the trainings. And if you have a data scientist, he knows already this story. So for the first training, basically we select not many, let's say not many iterations, not many epochs, and a quite fast training rate, learning rate. And when you push apply, it's a little bit accelerated for X. So when you push apply, what happens? You will get automatically, we start TensorBoard, we start the deep learning basically, and we open up for you the browser to monitor how the training is going on. I said 100 epoch, so it will go up to 100, and this is going automatically to show me how it's going on. So this is the ideal case in which everything goes well. You get the plateau. So this is going pretty well. So what does it mean? The video is a bit accelerated, but it means I have done a first training. I have saved my model here in this directory. So the output of the deep learning, what is it? It's a model that is written on disk. So there is no object in the project. There's something on disk that I can reuse later to do prediction. Okay. So indeed, what we save is a network with the weight of the network. I don't go to the details. So there are some files that represent the model that has been created. What I can do after a first training, I can start to do a first prediction to see how good is it. Of course, it has been done quickly. So probably the prediction may be not so good, but it's a standard things you want to check if the model is good or not. So you instantiate another module called prediction. You give the input, the grayscale, you give basically the model that has been saved on disk, and then you push apply. Yeah, you have to explain where is the network, the weight of the network, etc. So sorry, the model, not the network. You push apply, and this is faster, of course, than training. It's a simpler task to do prediction. Still, it takes a while. And you will get a prediction. What's a prediction? It's a segmentation using this model on the input you give. So if you give me a huge Berea microcity, it will be done on the entire microcity. So this is the predicted labels, and they are okay. There's some defect here, for example, because it's a first training. It's not perfect. It's not bad. So you can judge the quality with plenty of different methods. I'm not going to detail. You can, for example, just to give you some idea, you can compute the porosity and the permeability, this type of things on the predicted segmentation to judge if the segmentation is good or not. Because you may know by the lab what's the porosity and the permeability. And so you may do it digitally on the predicted segmentation and compare. This will give you a way to judge if your prediction is good or not. So if your model is good or not. Another detail important in deep learning, to do the training, you need a very good machine, a lot of GPU memory. To do the prediction, it's not needed. So you could have one kind of very powerful machine where you do your training. And then once you have saved this file, these are the model. You can do prediction on another machine with these models, and the other machine doesn't need to be a super duper machine. You still need a GPU, of course, but we have a sort of mechanism to adapt. The prediction is more robust to, it can run on small machine. The training is really an intensive task, so you need. So what I'm doing in the video here, I'm doing the second training using the weight that has been computed in the first training. So in a way, I'm not going to start again from scratch. The first training has got some good result. I want to improve it. So I will have to do some more intense computation for longer number of epochs with a smaller learning rate. And I'm going to start from the first training weight. So I say I create the result in the second training, but here I will give initialization using weights. So I will give the weight that I compute with the first training. Okay, that's the standard things we always do. So you have to master kind of two steps in digital rock. In deep learning. And you will use probably a smaller learning rate. We have also data augmentation for people that knows what is it. I try to quickly explain. You can generate some synthetic data from your input, like taking some patch and slightly rotating them. So if you don't have a lot of input to train your data, you can generate some synthetic data automatically. It's a standard things in deep learning to have data augmentation. Yeah, for monitoring, I can jump a little bit. I think I did play. So we start again our tensor board, and you will see the previous one and the new one. Okay, so you can select or not, and you will see the second one is trying to converge even better than the first one. So I accelerated because it was quite some time. I'm not going to comment what's the meaning of these spikes and so on. It's not the goal of the tutorial today. But I wish you see how it works for real. So, and now I do again a prediction with the second module, the second training. So then I can compare. Okay, so apply, nothing different. I can jump ahead. And I can tell you the second prediction, of course, is better than the first one. It's not always the case. If you do some error in the parameter of the deep learning, you may diverge and you will not get a better result. So this is a demo. Everything works nice. Deep learning is a lot of knowledge, a lot of time. But then when it works, it's really magic. Why is better than image processing, traditional image processing? You see the point here. I don't give any parameters. I just say, do prediction, please. And it doesn't really matter if it's, of course, it should be an image in the same class. I cannot do prediction of a sandstone and shale with the same model. So you have to train with the same class of rock to get result. With the same instance, train with the FIPSEM and try to predict a micro CT because they are not the same type of image. But if you remain the same class, so the other option you have is to do a recipe, a semi-automated recipe. Then every time you will have to ask to the user to trim some threshold. So you will need some interaction with the end user. Deep learning promise that you do a lot of work before, intensive computation, but then you have a model that, let's say, kind of magically predict on any data that looks similar to what the learning data. Okay, that's the point of deep learning. Well, this is a detail we offer into. So we have seen how to do segmentation with deep learning. On the Xtra portal, you have a very nice model, a deep learning model that will do SEM noise reduction. So this has been trained. Of course, we produce, as Thermo Fisher makes SEM. So we have a lot of SEM images, and we have been training this model, and we provide it for free. So it's another way of doing filtering so it's another way of applying deep learning. So I suggest you to have a look. Yeah, this is how it will. Okay, you see, this has been done many years ago, but you see the interface is a bit different. But the point is that you have this image, you instantiate the. I jump. You instantiate deep learning prediction. You load the model, and you just do apply. End of the story. You get the data filtered. So that's pretty amazing. And it will outperform other techniques like non-local mean or this type of things. So it's yeah. So this is a nice. It's a little bit old video, but it shows the capability of filtering of deep learning. And the plan is to have in the future more and more of this type of things in Avizo, to have more capabilities to do deep learning for different tasks. So today, embedded in Avizo, you have mainly in the current commercial version. Okay, so let's go back here. In the current commercial version, you have what? You have a module that does training and a module that does prediction, with the main goal of doing segmentation of multiple materials on grayscale images using this UNet model. The current commercial version is only doing it slice by slice. So every slice is handled separately. So we call it 2D stack deep learning segmentation. In the coming version, we will be able to do 3D deep learning. So meaning the model will really take care of adjacent voxel in 3D. So we think this is going to be even better. It will require probably more resources to do the training, but then the prediction will be better. So it's a natural evolution of the module. And long term, we hope to be able to offer deep learning for filtering, deep learning for segmentation, deep learning for processing, different type of flavors. Yeah, so that's the goal.